Hello everyone, this is Hasan, and I have a team member Yusuf Alfaifi and Charlton Sullivan. We are going to discuss petroleum oil life cycle. Today I'm going to discuss modeling of oil flow, integrating Darcy's law and Brinkman equation for efficient oil extraction. I will be discussing how we model the oil flow during the extraction, from the reservoir to the surface. We use Darcy's law and the Brinkman equation. These models help us optimize the oil recovery while minimizing the inefficiencies and environmental effects. Oil extraction involves three stages. Primary recovery relies on the natural pressure, and the secondary recovery uses the water or the gas injection. And the third one is enhanced oil recovery, which employs techniques like steam or the chemicals to maintain the reservoir pressure. To understand and optimize this process, we need to model models that account for the unique properties of reservoirs and flow dynamics. So now let's look at the factors influencing the flow in an oil reservoir. The key properties of an oil reservoir are the porosity and the permeability. The porosity determines how much oil the reservoir can hold, and while the permeability controls how easily oil flows through the rock, through the formations. For example, the sandstone formations have high permeability, making flow easier, while the shale formations with low permeability present challenges. And we talk about the geometry of the reservoir can also play a role, like the horizontal layers and the fractures can direct oil towards the wellbore, while bottlenecks or impermeable zones can hinder the flow. So the sandstones, for the uniform geometry, we say sandstone formations often have more uniform pore networks, making Darcy's law a reliable model for predicting flow. Now let's see how Darcy's law model this flow. Here is the Darcy's law is go-to model for flow in porous media. It relates the volumetric flow rates to the reservoir's permeability, the cross-sectional area of the flow, and the pressure gradient. The, we have a simple equation here. We use the Darcy's law to estimate the flow rates in high permeability reservoirs like the sandstone. However, it assumes laminar flow and does not capture complex effects near the wellbore or in low permeability zones. To address these limitations, we turn to the Brinkman equation. So we have a near wellbore dynamics with Brinkman equation. The Brinkman equation extends Darcy's law by including various viscous shear effects. It's especially useful near the wellbore where the velocity gradients are high and viscosity plays a larger role. We have a equation here. Uh, we have this Brinkman equation, which is a very simple equation, and this is crucial for low permeability formations like shale or when enhanced oil recovery techniques such as like water or gas injections are used. So Brinkman equation predicts flow more accurately than Darcy's law under these conditions. So after oil enters the wellbore, it flows upward through the casing. Let's explore this stage as well. In the well casing, flow transitions from porous to the free flow. Here Navier-Stokes equations describe single-phase flow, while the multi-phase flow models account for interaction between oil, gas, and water. Frictional losses in the casing are modeled by Darcy's Weisbach equation, and the key factors include pressure drop due to gravity, friction, and multi-phase effects. Accurate modeling ensures the pumps provide sufficient pressure to lift the oil to the surface efficiently. I have discussed cover the models for the oil recovery, and now I would like to request Yusuf to proceed further.
Hello everyone, my name is Alfaifi and I'll be talking about separation of petroleum hydrocarbons using nanoporous materials. Crude oil is a complex mixture of hydrocarbons categorized into alkanes, cycloalkanes, and aromatic hydrocarbons. Efficient separation of these components is essential for downstream applications such as fuel production and petrochemical synthesis. Traditional separation techniques like fractional distillation rely on boiling point differences. However, these methods are energy intensive and less effective for mixtures with close boiling components or isomers. Nanoporous materials offer a transformative solution. With their highly tunable pore sizes and selective adsorption properties, materials like zeolites, MOFs, and functionalized carbons enable precise separations based on molecular size, polarity, or chemical interactions. Adsorption-based separation leverages material properties to selectively isolate hydrocarbon components, such as shape-selective adsorption materials like zeolites allow separation based on molecular size and geometry. Polarity-selective adsorbents, including activated carbon and alumina, separate compounds based on hydrophilicity or hydrophobicity. Materials enabling bicomplexation, such as positive copper, modified zeolites, or MOFs, target aromatic and olefinic hydrocarbons. Compared to distillation, adsorption is energy efficient, cost effective, and environmentally friendly, with applications spanning fuel upgrading and pollutant remediation. Mathematical models underpin the optimization of nanoporous separations. The Freundlich adsorption isotherm describes the relationship between solute concentration and adsorption on heterogeneous surfaces. QE is the quantity of solute adsorbed. Ce is the equilibrium concentration of the solute in the solution. Sw is the solubility of the solute in water. K is the Freundlich adsorption capacity constant. It quantifies the adsorption capacity and varies across materials based on surface area and functional groups. N is the Freundlich exponent, indicating adsorption intensity. This equation provides a quantitative basis for tailoring separation processes. The Freundlich isotherm equation captures the nonlinear adsorption behavior on heterogeneous surfaces. The applications is characterizing adsorption for pollutants like aromatic hydrocarbons. Second is optimizing materials for high selectivity and adsorption efficiency. The equation delta VR equals VR minus V naught measures chromatographic performance. Higher delta VR indicates stronger adsorbate-adsorbent interactions, facilitating effective separation. By analyzing the retention volume across different conditions, researchers can identify optimal operating parameters. Example: using molecular sieves to separate N-alkanes from isoparaffins, researchers observed temperature-dependent detention behavior, revealing 180 degrees Celsius as the optimal separation temperature. K experiments on N-alkanes demonstrate the effectiveness of molecular sieves. Optimal adsorption observed at 180 degrees Celsius with 5A sieves. Space velocity studies showed higher desorption rates at increased flow rates. Graphs illustrate the relationship between temperature, flow rate, and adsorption efficiency, emphasizing the need for precise control of experimental parameters. Innovations in material science have expanded the toolkit for hydrocarbon separation. For example, metal organic framework, which has ultra-high surface areas and customizable chemistry, enables selective separations. Polymer adsorbents, which is lightweight, recyclable, and suitable for industrial scale applications. Composite materials combining properties of multiple adsorbents for superior performance in challenging separations. These advancements promise greener, more efficient processes tailored to industrial needs.
Okay, so we've discussed natural oil reservoirs as porous formations, and we have discussed the ability of porous membranes to act as mechanical separations to replace distillation for crude oil. Now let's transition to the application of porous flow models in the field of reactor design in the petrochem industry. So, when are porous flow models used when designing reactors? Well, the answer to that question is they are used when the reactors themselves are porous environments. Typically, this is the case when you're using a catalyst that is either on support or in packed nanoparticles, as you can see in the figure in the slide. And in the petrochem industry, these reactions look like hydrogenation, dehydrogenation, Fischer-Tropsch synthesis, catalytic polymerization and depolymerization, alkane cracking, and hydrodesulfurization, just to name a few. So why are porous flow models used in the field of reactor design? That's because we would like to determine a pressure drop, this dPdZ term here, and the best way to do that for design purposes is generally to use an empirical formula like the Ergot equation here. And the Ergot equation simply says that pressure drop per unit length is equal to some friction factor times the density of the fluid times the superficial velocity squared divided by the particle diameter of the packing. Um, and where the friction factor is a function of porosity and the modified Reynolds number, as well as these two empirical constants, 1.75 and 150, that just come from data fitting to experimental results. Uh, Also, these two additive terms are very important to understanding the Ergot equation and where it comes from, because this 1.75 term represents the inertial losses contribution to pressure drop, whereas the other larger term that's a function of the Reynolds number and porosity represents the viscous loss. Now let's look at some graphs to visualize the implications of the Ergun equation on reactor design and pressure drop. First, looking at superficial flow velocity and how that affects the pressure drop in a reactor. Superficial flow velocity is defined as the volumetric flow rate divided by the cross-sectional area, and we can clearly see pressure drop increases as the flow velocity increases, and it's a parabolic curve. It's the blue curve that you see on the plot. That's generally unsurprising, but we actually are able to break this down into two components, and that is the viscous losses of the orange curve and the inertial losses of the green curve. And we can see that the viscous losses are linear with respect to superficial velocity. The inertial losses are parabolic with respect to superficial velocity. And there's this crossover point at about 0.2 on this plot, um, but it will depend on other factors and units that you choose where this is specifically, but below which viscous dominates and above which inertial losses dominate the system. Somewhat trivial, but still useful observation to make is looking at varying void fraction or porosity. And we can see that obviously at a porosity of 0, no fluid can get through. But we see this really, really sharp decrease in pressure drop with increased porosity. And a big design consideration is finding that sweet spot where you maximize the surface area to volume ratio by packing as much catalyst as you can without overloading to a point where your fluid can't flow. Moving on to a slightly less trivial observation, we can see what happens when we vary density or viscosity. Now, varying density or viscosity isn't really a design parameter per se. It's going to be a function of your operating temperature and pressure, as well as the chemical species present in the reactor. But as we can see, uh, by reducing density or viscosity, we see a linear decrease in the pressure drop. But interestingly, we see these two y-intercepts. Now, why do we see y-intercepts? Why don't these converge to 0 as we approach 0 density or viscosity? Well, the reason for that is the inertial loss term is only a function of density, whereas the viscous loss term is only a function of viscosity. So if we ever reach 0 density, we see only viscous losses, and the same can be said about viscosity, where we see only inertial losses. And finally, as we're designing a reactor, let's look at the effects of reaction stoichiometry on pressure drop. So if we have an A to B reaction, this is assuming an ideal gas phase reaction, where we're not creating or removing moles from the gas phase. We see a linear increase with pressure drop with respect to position, unsurprisingly. And also unsurprisingly, if we have an A to B plus C, for example, cracking, or an A plus B to C, for example, hydrogenation, where we're either adding or removing moles from the gas phase, we see a relative increase or decrease in pressure drop. And the ease of modeling these changes with the Aragon equation is one reason it's preferred over more first principles models. Well, thank you for listening to our presentation. I hope you all learned something. Here are our references.